Hello everyone. In this set of lectures, we are going to look at a topic that I'm broadly defining as efficient embedded systems. And the goal over here is to sort of look at one step beyond the basic functionality that we want from an embedded system, and it is to see, okay, what are the things we can do in order to make it work efficiently, where the word efficiency has multiple meanings over here. It could be fast, it could be low power, it could be using a minimum of area, different kinds of combinations are possible. So let's look a little deeper into those aspects of designing and building an embedded system. So the first thing we want to do is sort of have a clearer definition of efficiency so that we know what we are working towards. And the primary idea that we want to address over here is that we have constrained resources when we are building an embedded system, and therefore these need to be used with care. And we want to make the best possible use of the resources that are available to us. So we could use this for functional definition of the word efficiency, which is to maximize the system performance while minimizing the utilization of resources within the system. Where a resource could be multiple things, it could be the CPU processing power, the amount of time taken, the amount of memory that is occupied, the power consumption, or it could even be just the cost associated with actually building and deploying the system, right? So there are multiple things that come in when we talk about efficiency or optimizing a particular metric, right? And what we are going to do over here is look at some aspects of embedded system design that could help us with achieving these goals. One of the first things that we need to understand in the context of what we mean by improving the efficiency of a system is two ways by which a particular embedded system could interact with the outside world. And these are usually referred to as the two contrasting styles of basically receiving inputs from external sources. They are called interrupts and polling. So let's try and understand the problem in the first place, right? This is a very common sort of problem condition that we deal with while designing embedded systems. We have some kind of a condition or a flag or a status register or something that needs to be monitored, and depending on what the condition is, we need to perform certain functionality, right? An example could be, has a button been pressed, or is there data present in a buffer when you are trying to receive from some kind of a communications device, or it could be, has a certain amount of time passed since the last time I checked something, right? Each of these is a condition. It could be expressed as a flag, it could be expressed as some kind of a register setting, it could be expressed in multiple different ways within the context of an embedded system. And as far as the design of the embedded system is concerned, I want to be able to check this particular condition, and based on whether a button was pressed or whether data is present in a buffer and so on, I either want to react to it, maybe process the data which is present in the buffer, or turn on a light, or change the state of my system depending on whether a button was pressed, or perhaps do something else. If I find that there was no data present in the buffer, maybe I need to again alert the user and say, hey, I'm expecting a response from you. Or it could be that I just move on and do something else after a specific timeout. But this sort of pattern, right, I want to check something and based on the status do something else, is a very common occurrence, especially in the design of embedded systems, primarily because of a certain degree of interactivity. We are sort of dealing with external stimuli, and this is a point that bears repetition. Embedded systems primarily are either interacting with humans or with other aspects of the external world, as opposed to, for example, pure computational programs. Let's say a high performance computing system like a climate model or an earthquake model that needs to be simulated and takes a large amount of time to run, where there is very little interaction with the outside world, right? In which case essentially all that the computer is doing is it's chugging away performing computations, but has very little to do in the way of actually receiving inputs or giving outputs except at specific times, and those could be under controlled conditions. In such a scenario, whatever we are discussing here probably does not even apply. But when you do have interactivity or the requirement to be able to respond to outside stimuli, this problem is a common pattern, and knowing how to deal with it is an important part of how you actually build an embedded system. So, the simplest possible approach would be something that is called polling, right? And in polling, essentially what we do is we repeatedly check the value, right? So, all that we are doing is just the simplest possible algorithm that you can think of, right? Go check the value. If the condition is satisfied, then yes, go ahead and do whatever it was required. If not, I don't know what to do, I'll go back and check again, right? So, this is literally what we sometimes call busy waiting, right? We are just keeping the entire processor extremely busy, doing nothing other than waiting for a condition to be satisfied, right? And literally the code for this would look something of this sort, right? If the value of a pin is low, then do something, right? Check the status of the LED. If not, then this entire code presumably is inside a loop where it would just go back and repeat the whole thing again, right? Now, this particular condition where we are basically checking for poll mode will become more clear when we look at the actual example that we are going to be considering in a short while, right? Now, before we get into the example and sort of look at how it gets implemented in practice, if you think about what this is doing, effectively what we are saying is I have an if condition inside a infinite loop, and that if condition is just going to get repeatedly checked. Every time that the if condition is false, that is, it's not satisfied, it basically means that I'm just jumping through here and then immediately coming back, right? All that the CPU is doing is checking a condition, branching, checking a condition, branching. It just pretty much sits in a tight loop over there, pretty much wasting time. It can't do anything else because it has to check for that condition to be satisfied, right? Now, on the other hand, the moment the condition is satisfied, of course, I immediately have a reaction. I have the ability to respond to it. And by making sure that I know exactly when I'm going to come back and repeat this, I actually get a fairly deterministic idea of when I'm going to respond to this, right? I can tightly control how quickly I'm going to respond to a given event just by saying that I make sure that this loop is as small or as I require, okay? So, polling is, from a programming point of view, clearly it is simple to implement, right? What's the problem? Of course, it's that the CPU cannot be doing anything else. And as you might imagine, if I just keep on repeating an instruction endlessly, the CPU is basically, it still has to go through the process of incrementing the program counter, loading the next instruction, maybe hopefully from cache memory or anyway from somewhere in memory, decoding it, figuring out what it is, checking the condition, and then jumping back and loading the previous instruction and repeating the same thing in a loop, right? Which basically means that there is a lot of activity as far as the CPU is concerned, and especially if I want quick reactions to my event happening, then the CPU actually probably has to be running fairly fast, which in turn means that it is most likely going to be consuming a fair amount of power, okay? So, polling, while simple to implement, may be problematic from the point of view of power consumption, right? This is something that we will look at a little bit more as we move forward, but intuitively at least you can hopefully see why that is the case. The alternative to this is what's called an interrupt, right? We have already seen what interrupts can do. Essentially what an interrupt does is it breaks the normal flow of the program. Pretty much at any point in time between two instructions that are being processed at the machine level, I could have an interrupt. And the moment I get an interrupt, what happens in this case is that I have something called an interrupt service routine, an ISR, which is a function, right? In general, it's written like a function in C. It is basically a piece of code which could be, normally we think of it as having been written in C, but it could be written in assembly language, it could be written in any other language, as long as it's already compiled and present in the memory of the system that I want to respond to this interrupt. And what do? We basically know that the interrupt that I get is associated with some kind of a number, right? Some identifier for the interrupt. And I have something called an interrupt vector table, which says, okay, if I get interrupt number 2, jump to this address. If I get interrupt number 3, jump to this address. If I get interrupt number 27, jump to this address. The number of possible interrupts, the number of entries in the table and so on are heavily dependent on the system that I am building. Some may have only the capability to handle a single interrupt, There may be others where you have a large number of interrupts. In general, having too many interrupts is also not a good thing. It complicates your design, it complicates the CPU, and it also makes it harder to actually write good code for such a system. But that's like everything else in engineering and design, it's a trade-off. Right? Now, the interesting thing about the interrupt is that because of the fact that an interrupt can come at any point and cause the CPU to jump to a new location and start executing instructions, I could be doing anything else with my CPU. I could actually be doing some other work, or in fact the CPU could even go to sleep. What exactly does sleep mean? It pretty much involves a state where I stop incrementing the program counter, I don't load instructions from memory, I shut down as many electronic parts of my CPU as I can. And the only thing that really is required over there is some piece of circuitry that says when this interrupt happens, load a new value into the program counter, get the system back into operation, whereby it's actually going to put the program counter value as an address on the address bus, get the data from there and start executing instructions. Okay. Of course, you can't do this without actually having hardware support, which means that if your hardware for whatever reason does not support interrupts, then you cannot use this approach. Having said that, pretty much any CPU that is available these days will have some kind of interrupt support. It's almost unthinkable to design a CPU that does not have interrupt support. There could be very specialized scenarios where you don't care about interrupts, but if you want something that is actually usable, you probably or certainly are going to have some capability to support the handling of interrupts. This is what the code would look like. You pretty much assume that your function, the interrupt service routine, is only going to get called any time that the interrupt actually occurs, which means that internally you are not even checking. You know that the interrupt occurred, the condition was satisfied, and you can straight away perform the function that was required, which in this case is basically just changing the LED state. Right? Interestingly, having something where you actually write something out into a serial port, for example, inside an interrupt service routine, is probably a bad idea, especially in an embedded system. And in order to understand why, you need to go back and recall what we discussed about interrupt service routines in the first place. They should be as brief as possible, right? Now think about what happens when you actually use a serial port in order to output data. If I have a serial port operating at 9600 bits per second, it means that for 1 byte, where I need to have a start bit, 8 bits and a stop bit, I will take roughly 1 millisecond to transfer 1 byte of information. And a string like this, which is roughly around 20 characters or so, right, is going to take up 20 milliseconds just to transfer data. Now 20 milliseconds with a clock frequency of even 1 megahertz is 20,000 clock cycles, right, which is much longer than the time required for actually handling the interrupt. Okay. So in general, inside an interrupt service routine, it's probably a bad idea to use any kind of printing or anything that involves interaction with the outside world, right? All those should be deferred to some other logging mechanism that gets activated as an event and gets processed as and when it's required, because the printing is not really very urgent. It could be handled later, right? But that's a digression. The main point is that the interrupt service routine itself is brief, to the point, and just does the work that's required. We of course have to explicitly say that this function, the button interrupt function, is the one that should be attached to the interrupt on the button pin, and the interrupt type is a falling level on that particular pin. That is, when the pin level goes down to 0, activate the interrupt. Okay. Now, how does all this look like when it actually operates in code? Let's take a quick look at the code corresponding to this. So once again, as usual, I have an example on Walkwe, and you can also create a similar code and test it out. Let's quickly take a look at this code. I have a few definitions up at the top of the thing, which basically says which is the button pin, that is to say which one is actually connected to the button in this case, right, and in turn will be used for generating the interrupts or will be polled. I also have an LED pin, which basically says which pin is going to be used for turning on an LED, right. The current state of the LED is also activated as a Boolean type variable and is set to low, right? And these are the aspects where, for example, Arduino type code has essentially added a few extra definitions to the C language. So low, for example, does not exist as a definition in regular C, but is a very useful definition when you are dealing with embedded systems, right? So this actually is a macro, a hash define somewhere in one of the Arduino libraries. And what I have over here is I have declared another variable called poll mode, which I initialize to be true. Now what do I do in the setup? I basically assign the button pin as an input, which has been pulled up by default, which means that the default state, if I was to monitor it, would be high. I set the LED pin as an output, and I start off by basically writing the LED state to LED pin. In this case it is low, which basically means that the LED pin is going to be off. I initialize the serial port and then just print out a couple of messages over here, which basically tells me, okay, if you find that I press the character 1, right, use polling from now onwards. If I press the character 2, use interrupts. Now what I do is, inside the loop, right, I have one piece of code which basically checks the status of serial. That is to say, it checks whether any input is present. And if the input is present, it reads from it. And if that input in turn was equal to 1, it basically detaches the interrupt from the pin. Okay. On the other hand, if the input was equal to 2, it attaches the interrupt, okay, and sets poll mode equal to false. Okay. Now what do I do with that? Immediately after this if condition out here, I then go forward and check if I am in polling mode. I go through and actually check the state of the digital button, that is the push button, right? If it's low, then I toggle the state. Why do I check whether it's low? Because every time that I press the button, I am actually connecting it to ground, and therefore the input will be seen as low by the processor, right? Remember that I had set it up as a default pull up, which means that the default state is going to be high, but every time that the button pin becomes low, it's going to actually end up triggering this particular poll mode condition. Okay, it toggles the state of the LED, writes that out, and then it basically goes into this thing where it says button pressed polling, and in this case it just basically delays by a small amount, right? And the reason for doing this is primarily to avoid something called bouncing. And what happens in the case of bouncing is that when you actually press a physical button, you will find that in reality it actually makes contact, breaks, makes, breaks a few times, possibly even like 5 to 10 times, all in the matter of a few milliseconds, right? It's too fast for a human being to even notice it, but as far as the computer is concerned, as we saw, 10 milliseconds is at least 10,000 clock cycles, if not more, right? So it's quite a long time for a computer. It's usually better that you sort of just delay and say, okay, I'm not even going to look at this button for a certain amount of time to avoid any problems with bouncing. Alright, so the polling part of it by itself looks fairly straightforward. The interrupt part is handled by this attach interrupt that we saw up here. And what it says is, it basically takes this digital pin to interrupt of button pin, which basically checks whether button pin can be handled as an interrupt source. And it says if it can, then basically take the function button interrupt and attach it as the ISR for this particular interrupt. And on what behavior of the button should I actually consider the interrupt? I'll take it on the falling edge of the button, that is when the button goes from high to low. What does the button interrupt function by itself do? It just basically toggles the LED state, writes that out, and in this case also prints a message. As I mentioned earlier, the message basically saying button pressed interrupt ideally should not be in an ISR, but here we are just using it for demonstration. Okay. Alright, so what do we have over here? I have set this up with a simple piece of hardware which basically has the Arduino in this case because it allows me to demonstrate things. You could do this with pretty much any other processor. In the case of Walkvi, you need to choose one of the processors where interrupts, for example, are supported. But if you actually have a processor that you are dealing with, let's say an STM Nucleo board or something like that, you can most definitely write your own code and actually see this happening in practice. Right? Now, one other thing worth mentioning over here is I have this button that I have instantiated, and it's connected between pin 2, as I mentioned out here, right at the top you can see that button pin is given as 2. Therefore, I have to connect this button to pin 2 of the UNO, and the other pin is basically connected to ground, right, on this push button. But the other thing that is worth at least mentioning over here, in case there's any confusion, is that you will notice that if I click on the button, apart from of course allowing me to change the the color of the button, it also has a checkbox saying bounce. I have disabled that in this case purely to demonstrate. What will happen otherwise if this bounce was clicked is that the simulator will actually simulate a kind of bouncing activity when you actually click on the button, which means that you will actually see the thing going through multiple up and down transitions. Okay. Alright, so let's run this code, and what happens is, as you can see right in the setup part, it basically printed out these messages. By default, poll mode was set to true, which means that if I now go and press the button, I see the message button pressed polling out here. I can press it any number of times, and if you look carefully, or if you were able to measure, you would notice that I can't press more than 5 times a second because I have this 200 millisecond delay sitting inside my polling routine. Okay. However, that's not very evident at first, right? Now, how do I switch it into interrupt mode? As you can see, if I input 1, it would go into polling mode, so I need to input 2. How do I do that? I can basically go into this small box at the bottom here, press 2, and in this case I actually have to press enter so that it goes through into the Arduino. It sort of works in line buffered mode, so unless I press enter, it doesn't actually transmit this information on the serial port into the Arduino. But the moment I did that, you can see that it has switched over to using interrupts. How do I know it is using interrupts? Because I can now click and you can see that it now says button pressed interrupt. Okay. And each time, of course, hopefully you have noticed that this particular LED has been changing state between red and off, right? The other LED that you see over here is connected to the TX pin of the serial port and basically lights up anytime there is a transmission of data. So ignore that for now, right? And well, hopefully we should be able to clear this, and you might see that in the case of interrupt, I don't have the 200 millisecond delay. So in principle, I would be able to see more button presses within a second if required. That, however, is not the main point, right? Because I could have removed the 200 millisecond delay from polling and still got it working. Where this really becomes useful, of course, is when I actually have a scenario where I don't want to be sitting here in a loop just checking the state of the button, right? I would like to be doing something else. And at the same time, anytime that the button is pressed, I want an LED to be turned on or turned off. I want some reaction to it. Okay. So, like I said, this is just an example to show how the code can be written for both polling as well as interrupts. Hopefully, most of you have also made an interesting observation over here, which is the fact that this particular line of code on line 19 is also implementing polling, right? Essentially what it's doing is it's checking within a loop whether there is data present in the buffer, and if it is, it does something. If not, well, it just moves on, right? And that is typically exactly how polling works, right? So even though the code itself was written in such a way that I actually wanted to demonstrate that polling could be used to check the state of the button, purely by coincidence, it also turns out that the very act of sort of allowing me to change between polling and interrupts is made easy if I actually use polling in order to find out whether there was data present in the buffer, and if so, to respond to it. Could this have been handled with an interrupt? Most likely yes. You'll have to check on whether the Arduino serial library actually supports an interrupt based on whether data is present in the buffer, and if it is, then by all means you could have also attached another interrupt which says that anytime a character is pressed, do something, right? So both of these would allow your actual loop to be performing other work, or possibly not even doing anything, actually basically just going to sleep, right, in the case of interrupts. And the interrupt by itself just sort of wakes up the system, does something, and then goes back to whatever it was doing earlier. Alright. So now we know that polling and interrupts are two ways by which I can process input from the outside world. The advantages of polling are, it's very simple to implement, right? And it also provides you with deterministic timing. What I mean by that is, you know exactly how long in general the loop is going to take, which means that between the time that an event occurs and the time that I am actually going to register it and process it, I can pretty much put a bound and say that within so many milliseconds I should have responded to the button being pressed, right? And in most cases that is what real time means. As long as I can provide a good level of confidence that within so many milliseconds I am actually going to respond to whatever you wanted, that's good enough. It doesn't have to be very fast, it only has to be within the constraint that has been set. Now there are obvious disadvantages to polling, the most obvious one being that the CPU is busy all the time, it's just checking something repeatedly, not doing useful work, so to say. There is also a potential for missed events. You might have noticed in the case of the 200 millisecond delay that if I clicked more than 5 times per second, the message would still get printed only 5 times per second at most, right? Now where things start to get really confusing is, let's say that I have multiple different external events and I don't know which one is going to happen at any given point in time. Perhaps I want a system that should respond either when a key is pressed or when timer expires or when some other sensor detects a particular event occurring. You now have multiple conditions to check for and your loop can start to get more and more complicated. It's also not, you might have a scenario where different events occur at different periodicities and need to be checked with different granularities, right? Maybe one of them you need to check only once a second, whereas something else needs to be checked once every 10 milliseconds, right? If so, you put all of them in one loop and suddenly you are checking the once a second event 100 times more than required, okay? So polling can get complicated if you end up having multiple events that you are trying to handle, right? What about interrupts? The obvious advantage is pretty much all the disadvantages of polling are now advantages in the case of interrupts. You have efficient CPU usage, right? Meaning that your CPU could be doing something else. It might either be doing useful work or it might even have just gone into sleep or a low power mode, right? And the other thing is you can make it arbitrarily responsive to events, meaning that you could actually say that every time the interrupt happens, as long as the interrupt handling routine is brief and quick, you can actually respond to another interrupt that comes immediately after that interval, right? Now even there, of course, there is a possibility that things happen so fast that you start losing events, but in general it's possible to handle it slightly better than in the case of polling without incurring too much of a overhead on the CPU cost. Now the disadvantage is it is more complex code. Interrupt service routines have to be designed with care, right? Because they need to be brief, they need to be quick, and in some cases it may not be possible to actually finish the work quickly, which means you might have to trigger an event or a notification which in turn runs some other background task or triggers another background task which then has to perform processing. So the coding can get more complicated. They are typically also harder to debug because even emulating such a system where you have multiple different interrupts happening asynchronously, meaning that you don't know when exactly they are likely to happen, can be very difficult to even simulate the exact behavior that you want. And there can be scenarios where if an interrupt happens in the middle of, let's say, a high priority, or an interrupt comes from a high priority item, but while a low priority task has an exclusive hold on some particular resource, you can end up with the problem of priority inversion that we had discussed earlier, right? So things like that can also potentially happen with interrupts, whereas with polling, the code is simple enough that you know that only after exiting the low priority task you are going to be looking at the high priority task. Yes, there is a delay, but it's a known part of your design at least. So what are the use cases? When would you use polling versus interrupts? The simplest case for using polling is to keep the code simple, right? When you have non-time critical systems where it doesn't matter whether you have responded within 10 milliseconds or 50 milliseconds and you are unlikely to miss an event because the frequency of the event occurrence is low in the first place, right? Those are good candidates for polling. And more than that, let's say that you have a limitation on the number of hardware resources. Maybe you have only 1 or 2 interrupt lines and they are already connected to some other important event handlers, right? So all of these are sort of good candidates for using polling. The other related thing, of course, is that your timing is fairly deterministic in the case of polling. You know that once every second or once every 200 milliseconds, you are going to come and do the condition check, right? Whereas with an interrupt, of course, as and when the event occurs, you will respond to it, but when exactly is it going to sort of check and be sure that something has occurred or not occurred, you can't be sure of that, because it all depends on when the external event happens in the first place. An example of where polling makes sense is, let's say you are doing a weather station and you want to monitor the temperature at regular intervals, right? You know that you basically need to just poll once every second, right? Check on a particular sensor and write the value out somewhere else. Now the interesting thing is, this is actually a place where you might even end up combining interrupts with polling. And what I mean by that is, you might actually have an interrupt that wakes up your processor once every second. The point is, I don't actually need an interrupt from my temperature sensor itself. What I will do is, as and when my processor wakes up, it will check, okay, 1 second has passed since I last checked the temperature sensor. Therefore, go read the value of the temperature sensor and log it somewhere, and then do something else or go back to sleep or do whatever you want, right? But the point is that every 1 second there has to be some way by which I sort of go check the value of the temperature sensor and then decide what to do with it. Now on the other hand, when do interrupts make sense, right? When you require immediate attention. Examples could be when you have external or unpredictable events. Short duration events that could be missed by polling, right? Something which just occurs for a very short amount of time, and perhaps the time in between your polling loop, right, was long enough that somehow the event, let's say it was a button press or some other kind of a short duration event, it went high and then went low within the time that you were actually finishing your polling loop, and therefore you missed the event completely, right? And of course, whenever you need CPU efficiency, meaning that you either want the CPU to be able to just idle or go to sleep, or you want it to be doing something else that is actually useful rather than just sitting there and checking a particular condition, right? And an example of this could be a motion sensor. You don't want to be checking a motion sensor once every second, because 1 second, for example, might actually be enough time for a person to even, let's say, break into a house, whereas if you had the ability to trigger an alarm within the time that you had, right, it might make a difference, or possibly shut down a bank vault like you see in movies, right, where within 1 second you need the vault doors to be closed. Of course, that's an extreme example. More important examples would be things where time is actually critical. It could be, let's say, an obstacle that a sensor in a car has detected, and you need to hit the brakes immediately, not after 1 second, right, not even after a few milliseconds, because that can make the difference of several meters, and deciding whether or not you actually hit the obstacle or you manage to stop in time, right? So these are the typical use cases where polling versus interrupts would be used.